Thank you, respected Chair, and very good morning to the audience. I would like to give special thanks to the organizers who have managed this virtual conference during the pandemic. Here, I'm Nafis Mansoor from the University of Liverpool, Bangladesh. My co-author is Ms. Sharmin Akhtar. Anyhow, the next 30 minutes or so, I'm going to talk about our paper titled A Spectrum-Aware Mobility Pattern-Based Routing Protocol for CR-VANET. Before moving forward, I'd like to give you an idea about the flow of this presentation. First, I'll be talking on the background and the motivation of this research. Then, the existing works will be discussed in the literature review section. Afterwards, the proposed routing protocol for CR-VANET will be discussed. Since we have done some experiments on our work, so the results will be discussed, and eventually I'll finish my talk with the conclusion and discussion on our future plans. In today's techno-driven world, every now and then we are having new wireless technologies where these technologies they require new transmitting frequency or operating frequency. But the problem is like most of the frequency bands they are already allocated to some entity. If you look at this particular picture where the frequency allocation chart for Bangladesh has been presented, where we may say that like all the frequencies are, most of the frequencies have been allocated. So we don't have any free spectrum. There is another problem with the current frequency allocation plan, that we are not utilizing the frequency properly. In some studies, it has been seen that the frequency is underutilized up to 70%. The term cognitive radio was coined by Joseph Mitola. Cognitive radio is nothing but a radio system that senses and recognizes the operating communication environment and afterwards dynamically adjusts the frequency, transmitting power and data rates. When the vehicles talk with each other, they form the vehicular network. So a vehicular ad hoc network is a network of vehicles where the vehicles they talk with each other wirelessly, and this sort of networks are the integral part of the intelligent transport system. In this slide, we'll see some of the applications for VANET. Monitoring the traffic, prevention of collision, traffic congestion, real-time emergency messaging are few of the applications for VANET. So we may say safety-related applications as well as to improve passengers' comfort would be the main objective for intervehicular communication. Moreover, if you consider the COVID-19 pandemic, autonomous car or driverless car are becoming more appealing. Besides, we may need certain vehicles that may deliver food or medicine while ensuring the social distancing. Besides, if you consider emergency situations, cognitive radio can play a vital role. So when you consider the routing protocol for CR-VANET, the protocol needs to ensure faster and reliable data communication with lesser packet drop and higher link stability and security. These are few of the works that have been studied in this research. The performance metrics were distance, mobility, reliability, link quality, and traffic density. An analysis of the literature review will be presented in the next slide. Though most of the major routing challenges have been addressed in the existing routing protocols, however, dynamic mobility of the vehicle, stochastic nature of the spectrum, and nose reliability are yet to be considered thoroughly in these routing protocols. Before moving forward, I would like to give you an overview of the proposed routing protocol, which happens to be a reactive routing protocol for CR-VANET. The protocol will ensure faster and reliable routing paths for communication. While selecting a route, the protocol will consider distance, speed, and direction of the vehicles, as well as number of available channels between two vehicles and the reliability of the vehicles. Here we have the network model. So we considered cognitive radio enabled vehicular nodes. This node can utilize the free spectrum where there would be two transceiver in each vehicular node. The primary user traffic is modeled over semi-Markov often process. Furthermore, we have also considered the communication ranges for all the nodes will be same. There will be a communication between two nodes when they share at least one channel, and each vehicular node senses free spectrum independently. In the proposed routing protocol, dynamic behavior of the nodes as well as the stochastic nature of the spectrum have been considered. Besides, we have introduced a new metric called NHDF, which implicitly considers mobility pattern, number of shared channels, stability of these channels, and node reliability. In network, as stated before, every VANET calculates the next of determination factor, that is the NHDF, based on an equation. That particular equation has been presented in this slide. As you may see here, to calculate the NHDF, a node needs to consider total number of channels, the transmitting weight, and the reliability factor. Besides, in order to calculate the transmitting weight, a node needs to consider the transmission range, the displacement, speed of the vehicle, and the cumulative sum of the link delays in the route. Now, in this slide, we'll see the working procedure of the proposed protocol. Since this is going to be a reactive routing protocol, so the source node needs to initiate the route discovery process, where the process will be initiated by a broadcast message. This message will be received by the one-hop neighbor of the source node. If the destination is not in the one-hop neighbor, those one-hop neighbors will again broadcast that route discovery. Meanwhile, prior to the broadcast, each node will calculate its own NHDF. Anyhow, this process will continue till the message reaches the destination. Once the broadcast message reaches the destination node, it replies back with its own NHDF value. Then, whenever a node receives this reply message, it will add its own NHDF with the message and it will reply it back. And such process will continue till the message reaches the source node. Now the source will construct the routing paths. However, if there are multiple routing paths, then the path which consists of lowest NHDF will be selected. Now in this slide, the proposed routing protocol will be presented using a graph. In this particular graph, you can see we will have several nodes. Here in the graph, S is the source node and D is the destination node. As we can see, there is no direct link from the source to the destination. Hence, the proposed routing protocol needs to identify the best route from the source to the destination. For this particular case, we will have several paths from the source to the destination. For instance, there is a path SABD, or there is another path SACD or SECD, as well as SCD. As in the previous slide, we have seen for this particular case there were multiple paths, so the proposed routing protocol identifies one single route from the source to the destination which can provide the best performance, and for this particular case it is SCD. It is worthwhile to mention here that the route selection is completely based on the NHDF value, where route with least NHDF will be considered as the final route or the selected route. Now, the performance of the proposed routing protocol will be discussed. In order to evaluate the performance of the proposed routing protocol, we have conducted some simulations. For this case, we have considered Network Simulator 2 as our simulation tool. In the simulation environment, we have also considered the total number of channels to be 100, and the area of simulation is 4000 meters square. The simulation runtime is 150 seconds, and as stated earlier that we have considered same transmission range for all the nodes, so for this case it is 500 meter. We also consider that these nodes will move with a maximum speed of 2 meter per second in the simulation area. Furthermore, for comparison, we have considered packet delivery ratio, end-to-end delay, and throughput to be our performance metric. In this study, the packet transmission delay is defined as the average time required for transmitting data packets from the source node to the destination. Minimum packet transmission delay is preferable for the best performance of the network. As we may see, the proposed routing protocol is giving least delay comparing with the other three protocols. Moreover, throughput in this study is defined as the number of successfully received data packets at the destination in an unit time. The unit for throughput has been considered as kilobit per second, and the maximum throughput is preferable while designing the routing protocol for CR-VANET. As we may see, the proposed routing protocol is giving the highest throughput for all the cases comparing with the other three routing protocols. Similarly, if you consider the performance of the proposed routing protocol, it has been found that the proposed one has given better performance in terms of packet delivery ratio comparing with the other three routing protocols. In a nutshell, we can conclude that the proposed routing protocol considers the double-folded dynamic behavior of the network, the autonomous movement of the vehicles, and changing spectrum availability are the dynamic behavior in the network. Hence, the routing protocol introduces a parameter called NHDF that implicitly considers mobility pattern, number of shared channels, link quality, and nodes reliability. Even in the simulation, we have found that the performance of the proposed routing protocol is better comparing with the other routing protocols. Since we haven't considered energy in our proposed routing protocol, so considering energy efficiency in a routing protocol for CR-VANET is our next research venture.